and go from the current slide. Okay, this is where we'll be starting, but we're not quite ready to start yet. I do have, well, first let me find out, do y'all have any questions, issues, concerns, problems that you want to bring up? Anything? Yes, I have. Let's see who's talking. That's Matthew. Yes, I have graded your test. I just haven't gotten it posted in Blackboard yet. Yes, I have graded it, and you did quite well. I'll just put it that way. I don't want to give you a score for everybody else to hear, but yeah, you did well. So don't sweat it. You're okay. I've gotten everything that I printed graded so far, but I'm not sure if I'm up with the printing. And that leads to another issue, so let me go on and get started on that issue. I think I went over some of this on Tuesday, but let me go over it again just to let you know. The very beginning of the term and the very end of the term are always hectic. But these weeks right in here at midterm sometimes can be quite bad too. And Matthew, you probably know this firsthand because Matthew was in also my first mini-term physical science class. And Matthew was very good about getting his stuff in on time, but a lot of the other students were not. And I was receiving last week and last weekend, which was after the term was over, I was receiving scads and scads of old labs, old tests, research papers, final exams, just everything was coming in just about at the same time. Okay, and therefore, because I had to have those grades in by noon on Tuesday, and I was going to be teaching at noon on Tuesday, I had to have them in Monday evening, so I was completely covered up in trying to get that class completed. And at the same time, I was trying to get set up for the second mini-term class, which started on Tuesday, so I had tons of things to do for that as well. Changing a syllabus, changing my locator card, you know, those kind of things, and just getting all the stupid stuff they have us do in Blackboard done to be ready for that class. So this week started really, really hectic. Okay, now let's back up a little bit from there. Last Friday I had to go in for blood work because I had an appointment Tuesday with my hematologist, and we saw the results over the weekend and they were not good. I mean, it's nothing to worry about. It's been there before. My white counts are skyrocketing. Okay, so I knew I was going to need a treatment. Well, I knew I was going to need one anyway. Okay, but the bad news was my red blood cells, my hemoglobin, and hematocrits and platelets were all tanking like crazy. Now, part of that is probably because the white cells are crowding them out. So, but usually they're not as bad as what it is now. So it was a double whammy. So when I met with him on Tuesday, he was pretty concerned about it and definitely need a treatment, but he wanted to make sure that what he's been giving me, which has been very, very effective so far, is still the best treatment for me. And part of the reason for that, the last time we had it, I've had this same drug for several times, so it's a monoclonal antibody. It really wiped out their white blood cells like crazy, but it also had some effect on the red blood cells, hematocrits, hemoglobin, and platelets, knocked them down too. So I was very, very anemic after that treatment. Well, as it's turned out now, I'm very, very, very anemic before the treatment. So that's why he's a bit concerned because of what happened last time. I can't afford to go too much lower on those other things, or else I'm in pretty serious situation. Not really bad. I'm making it sound worse than it is. I feel fine, except, and it's been creeping up on me, so I didn't notice it. But now that I found out what my red blood cells and stuff, I thought, oh, that's what I've been feeling. You know, I have been really, really tired, but I thought it was either I was working too hard or getting too old or something. I worried that it might be some exposure to corona or something like that, but not a very serious one. But I didn't know what it was, but now I know it's because my red cells are so low, my hemoglobin's so low. So I had to go in yesterday to get more blood work done so he can tell if the current treatment's the best one, and also to make sure nothing's going on with the red blood cells that he can identify. So he's studying the white cells with half of the things he took yesterday and studying the red cells with the other, and probably platelets with one too, I don't know. So anyway, it's about a 48-hour turnaround on this one, so I'll know sometime tomorrow what's going to be the deal. Okay. Now, why am I telling y'all this? Okay. Besides getting sympathy. No, that's not what it's about. Here's what it's about. Because it's been more than 9 months since my last treatment, if he goes with the same treatment he's had before, which like I said has been very effective, though it did damage some other stuff too, because it's been more than 9 months, they want to do it in 2 parts like we did the very first time I took it. He's going to give me 10% the first day and 90% the next day, which is bad news because I usually have my treatments on Fridays, which would have been fine. Except now he needs them 2 days back to back, which means Thursday and Friday, and guess what that means for y'all? It could be, not necessarily is, but could be some Thursday coming up soon, as in maybe even as soon as next Thursday or some Thursday coming up soon, I'm going to have a treatment. And I have no idea when it's going to be scheduled. If it's scheduled in the morning, it's going to wipe out this class. If it's scheduled in the afternoon, it'll wipe out my afternoon class. But it is going to wipe out a class sometime on a Thursday. Then on that Friday, I will be out of pocket altogether, so I won't have any office hours on that Friday because I'll be at the clinic all day. The 90% will take all day, basically. Okay, so it does have an impact on possibly the class, definitely office hours, but we don't know if or when it's going to happen. Okay, so I did want to let you know that. Now, on top of all this going on this week, a very good friend of mine, she's in our Sunday school class, we've known each other for decades, she collapsed. She's older than I am, believe it or not, 76. She collapsed in the parking lot of the church on Tuesday night and was rushed, to emergency room, and she is in critical condition. And I'm her contact person. She has no living relatives anywhere close. She had a sister living in Virginia who was many years older than her, so I don't even know if the sister's still alive. They were not close, so I'm her contact person. So I have been dealing with that ever since Tuesday night. Also, the hospital, the social workers, our Sunday school classmates, the people at church who were with her when she collapsed, they've all been contacting me because I can get more information than most of the rest of them can, and I can't get much. And what I've been getting has been contradictory, or confusing at best, okay? One time I'll hear one thing and the next time I'll hear something very different. So there's been all that going on, which I'm going to try to keep from interfering with classes, but sometimes I may not be able to keep it from interfering. If something happens that needs an immediate response, then I'm going to have to deal with that immediate response. So it's been quite a week. But that was a very long answer to your very simple question. But the test is graded, but that's why I haven't had a chance to put all the grades on Blackboard. And the other thing is, and it's just been driving me nuts, this really idiotic template that they make us do, and I'm teaching too many classes. I know that. I've got 7 classes now. I just finished one, picked up another one, so I got 7 classes, and I'm having to do this template stuff every week for all 7 classes, and that eats a lot of the time that I would have been able to spend grading papers and putting the scores on Blackboard. So I'm getting caught up again from the weekend because it was a horrendous weekend with the ending of first mini term and starting second mini term. So I'm almost got my head back above water when all this stuff is happening now with my health and also with my friends. So it's been quite a week. So any other questions? Hopefully my answer won't be quite as long as that. Any issues, concerns, problems, anything else like that? Okay, if not, we're in chapter 4, trigonometry, almost through with chapter 4. We're in 4.8, which is the last section in chapter 4, and we are on example 2 on page 328. And here it is on the PowerPoint, so we can work it here. Now, here's the deal. This example 2 on the PowerPoint is not example 2 in the book, okay? And there isn't an example in the book like this example 2 on PowerPoint. So we're going to do the example 2 on PowerPoint. It's somewhat similar to some of your exercises at the end of the chapter. Then we'll go back and do example 2 in the book, and we'll go on from there. So here's example 2 on the PowerPoint. A safety regulation states that the maximum angle and elevation for a rescue ladder is 72 degrees. A fire department's longest ladder is 110 feet. What is the maximum safe rescue height? So in other words, let's just assume this is the ground. Now one of the assumptions here is it's fairly level. My ground isn't very level. And here's your building going up here, okay? How big a building it is, we don't know. Okay, here is the fire truck down here. I'm not going to draw the fire truck. But we have a ladder from the fire truck that goes up 72 degrees. So let's just imagine that 72 degrees. Okay, now this ladder is 110 feet long. Okay, now what's the maximum safe rescue height? In other words, how high up the building can you go? This is the unknown. Okay, the question is, how do we solve this problem? Is there any trig function? Since you got an angle in here, you think trig function, and that's what we're studying, right? Is there any trig function that relates this side? And now here's another assumption. We're going to assume that we have a right angle, that the building is going straight up and the ground's fairly level. So that's a right angle. So this will be a right angle, okay? Is there any trig function that relates this angle to that side and this side of that triangle? Anybody? Oh, here's Morgan coming in. Let me get her here while y'all are pondering the question. Okay. Morgan is here. All right. That was your time when they played the music on Jeopardy. What's your final answer? Anybody? What trig function relates this angle, this height that we're looking for, this length that we know? Anybody? Well, if this is your right angle, that makes that your hypotenuse. Okay, now I wish I hadn't used H here, okay? Well, if that's your hypotenuse for this angle, that's the opposite side. What trig function relates this angle to its opposite side and its hypotenuse? Anybody? Some old hen. Now this is the hypotenuse hen, so I probably shouldn't use that. That would be H over 110. I'll go and put the feet down here too. How do we solve for H? Multiply both sides by 110 feet. Okay, and that makes H equal to, not one I can do in my head. So I'm going to pull out my handy dandy phone, which serves as my calculator. Uh-oh. I don't know when it happened, 14 minutes ago. It must have been right before class started. I got a call from the social worker. That could be bad, but I'll wait and call her later. Okay. Sorry about that. It gives me a sinking feeling. Okay. Okay. So what we've got is 110. Oh, I need to turn my phone sideways so I get scientific mode. Say 110 times. Now on my calculator, since it's a telephone, I have to enter the degrees first. Well, I have to be in degree mode. And since this doesn't say radian at the top, it says it down here. This is how I get to radian mode. This doesn't say, so that means we're in degree mode, so I'm okay. So I'll put 72. I have to enter that first, and then the sign key near the bottom there, and then I hit equal. And I get, here's what the answer says. What is the maximum safe rescue height? This says, my calculator says 104.6162 blah blah blah. Since we're dealing with safety issues, this is one time I will not round up, round like I'm supposed to. That would get me higher than the maximum safe height, so I'm going to leave it as 104 feet. Now they may say 104.6, okay, or something like that. Hey, if I'm on that ladder, I want to be super safe. So 104 feet is what I get. Let's see what they, oh, they don't have a got, okay, but we'll see what they got on the PowerPoint. Any questions on that, the way I did it? Okay, I'm going to clear the slide then, and let's see what they did. They drew a much prettier picture than I did. Here's the sketch, and there's your 110 feet. Here's your building, and it's from the top of the truck. When I used to do this, I put the ladder on the ground, then I realized they had it on the truck. So it's followed from the formula. The sine of this angle A, I just called it 72, is the adjacent side, the opposite side, which why do they call it A, I don't know. Oh, because they called this angle A, this is little a. Hypotenuse is C, the right angle is always C, hypotenuse would be little c, that would be A over C, and that makes A equals C times the sine of theta, which is 110 times the sine of 72, which is 104.6 feet. They didn't put that in, so the maximum safe rescue height is about 104.6 feet above the height of the fire truck, which if they're putting on a fire truck, yeah, that's right. All right, any questions on that? Same type answer we got. Now, they're skipping their example 2, their example 3, and their example 4. So we'll do those on our whiteboard. Okay. So let's pull it. I'm going to actually go back a slide and pull up the whiteboard from here. Not that it matters, but just, okay. Now I've got to make some adjustments to the whiteboard here. They put the taskbar in the white space, which makes no sense. And because I have your names and stuff like this over here on the right hand side, you can't see that, but I can. I'm going to move the whiteboard as far to the left as I can to give me the maximum amount of white space. Okay, I'll move it up as far as I can because we have these other things that keep popping up there. And something else that popped up is that James is here. So let me get James marked here. All right, we got James. So let's move with James. We're on in the book, Chapter 4, Trigonometry, Section 4.8, Applications and Models, last section in this chapter, on page 328, and we're at the bottom of the page, example 2. Now we just did it in example 2, but that was on the slide set. This is a different example 2 in the book. It's not on the PowerPoint. So the height of a mountain is 5,000 feet. And they show the graph here too. So I'm going to try to draw the mountain. Okay, I'm going to start with assuming we got level ground down here somewhere. And again, my ground is not very level, but of course ground never is perfectly level. So let's just assume it's fairly level here. And here on the ground here somewhere, if I can get my pen to come back over, we have some mountain. Okay, there's the mountain, and we have the height of this mountain to be 5,000 feet. Okay, that's the height of the mountain. Okay, the distance between its peak and that of the adjacent mountain is 25,000 feet. So I'm going to try to draw the adjacent mountain here, and obviously I've not drawn to scale, but there's the adjacent mountain here. Okay, so from this peak to this peak, let me make sure I've got enough people here. We have 12 students here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, got everybody here. From that peak to that peak is 25,000 feet. Obviously, I'm not to scale. That's not 5 times the height of the mountain, but this will be the 25,000 feet from this peak to this peak. Okay, that's a lateral, horizontal distance. The angle of elevation between the two peaks, so you're standing here on the top peak, measuring, let me get this out of the way, with a sextant looking at the peak over here, and you determine that, whoa, that's supposed to be horizontal here. This is 27 degrees. Angle of elevation is 27 degrees. What is the height of the adjacent mountain? So we're looking for this height here. And again, I will call this H. That's the unknown. That's what we're looking for. Well, since you're on top of this mountain, you're really more interested in, here is the right angle that you have. You can tell from this how much above 5,000 feet the other mountain is, but this is 5,000 down here too. This lower part here is 5,000. I'm just going to abbreviate feet. This is from here to there. If I drew my line horizontally, which it probably isn't, but you get the idea. So the H we're looking for is the whole height. What you can get out of your trig is just this height here. Now, the way they did last time, they named this angle A. So this now will be our little a. That's not the same as H on this one, okay? H will be little a plus 5,000. Does that make sense? But in this case, we don't know this hypotenuse like we did with the ladder, but we do know this adjacent side, and we know that's the 25,000 feet. Okay? So now we know the angle, we know the adjacent side. Whoops, here comes iPhone. Okay. Let me see if I can remember who iPhone is. Hang on just a minute, folks. See if I can remember who iPhone is. Maybe I don't know who iPhone is. Who just came into the class under the name of iPhone? Somebody just came in. Who is it that came under the label of iPhone? Anybody? I know someone. Ah, is it? No. Who is it? Damien, got it. Okay. I don't think you've been iPhone before, have you? If you have, I didn't remember it. Okay. So got you here. Got it. Thanks. Okay. Now, okay, good deal. Damien, we're in chapter 8, chapter 4. Whoa, that was not what I wanted to do. Okay, that's what I wanted to do. Okay, we're in chapter 4, trigonometry, section 4.8, applications and models, and we're at the bottom of page 328 in example 2 in the book. We had an example 2 on the slide set, which was not this example. So that's what we're working on now, is this one in the book. Okay, and we've got it set up here, and the question that was before the class, before you came in, and they were waiting for you to get here so you would answer it. So what is the trig function that relates this angle 27 degrees to this height, or this height HA over here, that we need to determine the h that we're really looking for, and the side down here, which we know to be 25,000 feet. So this is the opposite side. Don't let the A confuse you here. That's the opposite side of this angle. This is the adjacent side of that angle. What trig function relates opposite side and adjacent side? There's actually two of them, but one we like better than the other. Anybody? Not just Damien. Anyone? It's the tangent. Tangent of 27 degrees is going to be the opposite side, which we're calling A, because we named the angle A, and over the adjacent side, which we know to be 25,000 feet. And they set this one up pretty nicely for you, because again, what we do is multiply both sides by 25,000. 25,000 times the tangent of 27 degrees is equal to A. Because when you multiply the 25,000 here, it cancels that out, moves it over there. So, time for the handy dandy calculator. Again, I'll need to be in scientific mode. So I'll take my calculator, turn it well, it didn't take, did it? There. Turn it sideways. I'm in scientific mode. And what I have here is 25,000, 25000. I have to be careful. I have fat fingers and little bitty buttons here. Times the okay, in this calculator I have to enter, make sure you're in degree mode. I am, okay? So I enter 27 degrees first and then press the tangent key. If you have a real scientific calculator, you'll probably do it in the other way. You press the tangent key and then put in the 27 degrees. That gave me 0.509, hit the equal sign, and that gave me the A height here is 12,738 feet. So this A here, according to my calculator, is 12,738 feet. Okay, now a word to the wise here. All these numbers are rounded to the nearest thousand, so there really is no reason to suspect we have more significant digits than they do. So I would almost be tempted to round this to 13,000. Okay, however, we'll leave it like this because I know the book doesn't pay attention to that. We have to add that to the 5,000 that the top first mountain was, which I'm not convinced it's exactly 5,000. They just rounded it, and that makes the second mountain, the taller mountain, 17,738 feet Again, I would have said about 18,000. Okay, let's see what the book says. I must have done something wrong. Let me punch it. It must have been my fat fingers. Let me try this again, because I didn't get the same answer they did. Okay, 25,000 times 27 degrees tangent, that was right, equal. Wait a minute. Okay, I misread the problem. I did misread the problem. Sorry about that. Okay. Their problem makes no sense. Sorry about this. But I wasn't reading it carefully. It said the height of a mountain is 5,000 feet. The distance between its peak and that of the adjacent mountain, I interpreted that to be the horizontal distance. That's something you can measure. Okay? What they meant is the actual distance from it, not the horizontal distance, but the actual distance. They meant this to be the 25,000. Now again, this makes no physical sense. Who in the world is going to have a tape measure that they can measure peak A to peak B? Okay? I don't know. So this problem is a made-up problem. I interpreted it to be, well, take the center of this mountain to the center of that mountain on level ground. Yeah, we can measure that and found 25,000 feet. That was not what the problem intended. So now, let's redo everything. So let me go up here and get my eraser and go to town with my eraser, if it'll come up. Okay, I know this is going to change, and that's going to change, and that's about it. Okay, because now if you're dealing with this, the opposite side and the hypotenuse is what you're dealing with now, that relationship is the sine of 27 degrees, and that's what we have here. Almost just like the previous problem, but it doesn't make as much sense. The fire truck ladder made a lot more sense than this one does. So let's go back to our calculator, clear the screen, get it turned sideways. Okay, and now we'll do 25,000 times, and again I have to enter the 27 first, and then do the sine of that one, which is 0.45, which is a little bit less, and that gave, oh, I needed to erase that too, didn't I? Okay, this changed, and this will change, of course. Okay. All right, that gave me 11,340 or 50 feet. 11,350 feet. That 49.7. I will round that one up to 50. Add the 5,000 to it, and you get 16,350 feet. Again, I'd say about 16,000 feet. Okay, and they get the same thing I did, 16,350 feet. Sorry about that. I wasn't paying attention to the book. I was working it in a way that made sense to me, not what they were really asking for. Sorry about that. Okay, I need to put my phone, not have to, but because I do know I've got a phone call coming up later on charge, so it'll be charged when that get here. All right, there is a checkpoint in the book. There's not a checkpoint for the first example 2 we did on the slide set, but there is for this one. And that's a lot like the one we did in class on the PowerPoint. It's not on the fire truck. It's a shorter ladder, but you can still do the same thing. So they skipped example 3. less clear. Anyone have any questions on this before I clear it? Okay, going to clear the drawing here, and let's do example 3. At a point, let me pull the book into my lap because it's hard to read from a distance there. At a point 200 feet from the base of a building, so here we have a building. If I can get my pen to show up, where are you, pen? There you are. So let's have the building here. Okay, and here you have, ooh, supposedly level ground here. Okay, and you're 200 feet from the base of a building. Let's just put you right here. And let's say this is 200 feet from the base of a building. Okay. The angle of elevation to the bottom of a smokestack. Now this is a very strange smokestack. It's here right on the edge of the building, and it's very, very tall. So the angle here to the point where you are, if I had drawn where you are right, is 35 degrees. Now mine looks like it's a little more than 35 degrees, so don't trust my drawing, just pay attention. Whereas the angle of elevation to the top is 53 degrees. Now that looks maybe a little more likely. Ooh, these shouldn't overlap, but that angle there is 53 degrees. Okay, as shown here. Find the height of the smokestack alone. This is what we're looking for. They named it S. Okay, now the first question that would come to mind, do we have enough information to solve this? And yes, we do, but it's not going to be a one-step process. This is going to be the good old Texas two-step here. Or 3 or 4. I don't know. I do know, but okay, let's see if we can figure this out. We have 2 angles here. This first angle, the 35 degrees, is going to give you the height of the building. So I'm going to put B here for the building. Now I'm not using the same nomenclature the book does. This is what I like to use. This is this angle here. Okay, so we have an adjacent side and an opposite side. This one does relate to tangent. So the tangent of 35 degrees is equal to the opposite side, B, which we're looking for, not as your final answer, but B, and then the adjacent side, 200. And again, they're dealing with feet. And they're also dealing with degrees. So this gives us that B, when you multiply both sides by 200, is equal to 200 times the tangent, I have to slow down my writing, of 35 degrees. Okay, so I will pull out my handy dandy calculator again, get into calculation mode, turn it sideways so I can get to the scientific notation, and do 200 times, since I have to enter the degree first, make sure you're in degree mode, 35 times, take the tangent of 35, that's about 0.7, and hit equal. Okay, so that's the height of the building, is approximately 140 feet high. 140 feet. Now, I like to pause here and ask, does this make sense? Since this angle here is 35 degrees, which is less than 45, it doesn't look like it is, my drawing isn't good, that means this height is less than your distance from the building, and it is. Good. That makes me feel warm and fuzzy inside. Okay, next we have the 53 degrees is measuring both the building height and the smokestack height. So that equation, and it's again going to be tangent, opposite over adjacent. So it's going to be the tangent of 53 degrees this time is going to be B plus S. Maybe I should say S plus B because y'all might think I'm talking about BS. I'm not. Okay. Over the 200 feet. Which implies, of course, that the summation of B and S is equal to, multiplying both sides by 200 again, 200 times the tangent of 53 degrees this time. All right, let's pull that up. 200 times, make sure you're in degree mode. I have to enter the 53 first, times 10, or not times tangent, take the tangent of that. That's about 1.327. Hit equal there. So this B plus S is equal to about, let me put approximately anyway, 265. 265 feet. Okay? Now, we're looking for S. This is the unknown here. Okay, that's what we're looking for. Well, we know B plus S was 265. B alone is 140. So let's subtract off the building from the total, and you get 125 foot smokestack. Okay, obviously mine was not drawn to scale. You knew that. That angle was greater than 35 degrees. So if we'd have had this down here and that up there, that would have made more sense. So don't trust my drawing, but trust the numbers. The numbers work. About 125 feet. They put the 0.4 on there. Since all you had was 200 down here, really, that's only one significant digit. How do you get 4? I was stretching it to get 3. I'm not going to go as far as 4. About 125 feet. That one also has a checkpoint. Please do the checkpoints. Okay? That will give you lots of more practice doing exactly what we did. I know I'll need this again, but I'm going to charge it every chance I get. Let me get a drink of water. Okay. Now, any questions on this one? Now we're going to move to example 4. So I'm going to clear the drawing here. 4 is still not on the PowerPoint. So here we have, let me get the book in my lap so I can read it better. And okay. I run out of energy so fast. Before I thought, well, I'm not sleeping well, something like this. Now I know I'm anemic. No wonder I'm running out of energy. Okay. A swimming pool is 20 meters long. Okay. Now I don't draw swimming pools well, so I'm going to try my best to draw a rendition of a swimming pool. Okay, that's the top of the pool. And we know this is 20 meters long. That's the length of it. 12 meters wide. 12 meters wide. The bottom of the pool is slanted, so that the water depth is 1.3 meters at the shallow end. So I'll put this as the shallow end here and make this as 1.3 meters. Now obviously this is not drawn to scale, and I don't know why the pen did that, but that wasn't me, it was the pen. At the shallow end, which is just under 6 feet, because 6 feet would be close, a little less than 2 meters, so this is shallow, okay? You could walk on it as long as you're not too short on the bottom there, okay, and have your head above water. And 4 meters deep at the deeper end. So let me go down to the deep end here. Yuck, this thing drives me absolutely bonkers. Okay, let's go down to the deep end here and make that 4 meters. 4 meters deep. So it's getting deeper as you go down here. Now I'll go on and do this line over here just so it doesn't look like it's hanging in space somewhere. Okay. As shown in their figure. Okay. Now, it says find the angle of depression in degrees of the bottom of the pool. So we need the horizontal here. Now this doesn't look like it's horizontal, but because I drew it sort of isometrically, we need the horizontal line here, which stays 3 feet. I'm sorry. Obviously, I'm not drawing the scale here. Okay. This is my 1.3 here, and that makes this here 2.7 because it adds to 4. So we're looking for the angle of depression. That's what we're looking for here. Find the angle of depression in degrees of the bottom of the pool. Well, this angle here, we know this length here is 20 meters, which makes this length here 20 meters, and this over here is 2.7 meters. Well, and by the way, what is your right angle? There's your right angle. So again, you have the angle here, theta, this length 2.7, that length 20. This is opposite adjacent. This is your hypotenuse down here. So we have, again, tangent of theta is equal to 2.7, the opposite side, meters, divided by 20 meters. Notice your meters cancel out, which is a very good thing, because when you take the tangent of an angle, you get a number, a pure number. And Damien's back under his own name this time. Okay, good deal. Glad you're back. Or at least under Damien C. Okay? So what we have to do here is get in calculator mode again. Be sure you're in degree mode and get it in scientific. Now what we've got here is 2.7. Question? 2.7 divided by 20. It's a pretty small number. Okay? 0.135. Now, what you have to do is take the inverse tangent of that number to find out what your theta is. If I could get my pen to show up. Where is it? There it is. So if you take the inverse tangent of this, okay, and take the inverse tangent of this, then I get to, on my phone, to get the inverse tangent, I go to the second key that's down here, or up here, right about there. You see it says second, so I press the second key. Now that changed my sines and cosines and tangent to inverse sine and cosine and tangent. So I'm going to take the inverse tangent, and I'm in degree mode of that number, 0.135, and that gives me an angle of about, and this is where I'm going to say approximately 8 degrees. Now I know the book is going to give some, well, let's see, maybe I'll give them benefit of the doubt. This is 2 significant digits there, 2 there, 2 there, 2 there. Oh, we imagine 2. Let's just imagine 2 there. So let's not do 8. Let's do 7.7. 7.7 degrees. Really, it's not very, the 20 is only 1, but we'll go to 7.7. The book, I bet you'll give it a lot more. They say 7.69. No way they have the justification to do that kind of precision with what they had. But all you need is get the close in government to work, right? And we are government, right? Which makes me remember, should be saying this every class, especially now. I hope you're registered to vote, because we're getting very, very close to the end of registration. We may already be past it. Maybe today's the last day. I don't know. But please, folks, vote. Okay? I think I told y'all before, my wife and I have already voted. Many people have already voted. Because of the COVID and other things like this, it's just, and we went down to the courthouse and we were able to vote. It took us about an hour. We didn't think it would take that long, but there was a fairly good crowd down there. Not huge, but fairly much. Other people have said it's taken them up to 3 hours. Other people are saying they can get there in 30 minutes. So it just depends on the luck of the draw. My wife tomorrow is taking 2 friends of ours because they are afraid they might not, they're older than we are, and they may not be hard to find parking close. So my wife's taking them. She can drop them off in front of the courthouse. She'll go find parking and then pick them up. So please, folks, it's worth the effort. Now, if you don't want to go to the courthouse in person, you can do an absentee ballot. You're probably getting pretty close to the deadline for that too. So please, please vote. This is too important not to. Okay. So anyway, we finished this. The angle of depression was 7.7 degrees. They put 7.69. There is a checkpoint there as well. All right. That finishes those. Any question on that in the book, example 4? Anyone? All right. Then we're going to go back to the slide set here, if I can get my pen to show up, and go back to 4.8. Go back to the slideshow. Okay. Oh, Courtney's here. Good deal. I didn't see Courtney. I hope he wasn't waiting too long there. Courtney's here. All right. That gets us up a pretty good number of people here today. That shows 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yep, I got everybody here. Okay. Still missing a few. Hopefully they will come in before the class is over. Okay. All right, we finished example 2, 3, and 4, ready for, if I can get the slideshow to click, trigonometry and bearings. Now this isn't the type of bearing that you use to make sure wheels turn smoothly or that kind. This is a bearing they talk about in navigation, in surveying, those kind of things. And trigonometry is used all over the place there. Okay. In surveying and navigation, directions are given in terms of bearings. Now, a bearing measures the acute angle. Notice that acute angle that a line, a path or a line of sight makes with a fixed north-south line. Okay? So, how do you get acute angles out of that? Well, so many degrees east of north, so many degrees west of north, or so many degrees east of south, or so many degrees west of south. Okay, so a bearing measures the acute angle. So you always mention which direction you're facing first, and this example is south, so we're facing south, and we're doing 35 degrees east of that. So that would be over that way. So the bearing of south 35 east, south is which direction you face, 35 degrees is how far to which direction you go. South 35 degrees east shown means, look, here's your compass rose, north, south, east and west. You have to know which way which is. You go south first, 35 degrees toward the east. This one is a north 80 west. Face north, go 80 degrees, almost 90 degrees to the west, and there you are there. This one's north 45 east, north 45 east. Notice all these are always acute angles. That one's just barely acute, but it is between 0 and 90. And always give the direction you're facing first, then how many degrees acute angle to either east or west. So you're facing either north or south, how many degrees to the east or west. Okay, make sense? Okay. Here's example 5, and this one is in the book. We'll go with it. Okay. A ship leaves port at noon. Here's your port over here at point A. Heads due west at 20 knots. Now, does anyone know what they mean by the term knot? K-N-O-T-S. Okay. A knot is a speed, and the reason they don't use miles per hour is that on the water, they don't use the same mile that they do on land. On land, they call it a statute mile, which is 5,280 feet long, or 1,760 yards long. That's a mile on land. On the water, they use a nautical mile, which is 2,000 yards or 6,000 feet. Now, you don't need to know that for the problem, but what a knot is a nautical mile per hour. So it's, when you say 20 knots, that's a little bit faster than 20 miles per hour, because a nautical mile is a little bit longer than a statute mile. So that's how you're heading due west at a speed of 20 knots. Okay. Now at 2 p.m., that was at noon. At 2 p.m., the ship changes course to north 54 west. That indicates this. So basically, you know how fast you are traveling here for how many hours. So that gives you 40 nautical miles on this base down here from A to B. Now you turn to north 54 west. Okay, I've got to sneeze. I'm going to try not to. It says find the ship's bearing and distance. Wait. Sorry. That'll blow your ears out. I tried to move my mic in time. I may not have gotten it. Okay. Find the ship's bearing and distance from port at 3 p.m. So that's 1 hour later. Didn't change speed, so still going 20 nautical knots, which is 20 nautical miles per hour in 1 hour. So you know your distance here is 20 nautical miles. 40 nautical miles here, 20 nautical miles here. Okay. Now what they're asking for is the ship's bearing at 3 p.m. from the point of interest. So you know it's going to be north so many degrees west, but we don't know how many degrees. Okay. Now, what your triangles show here, okay, is that the only angle you have, well, you know this is due west. You know this is 54 degrees west of north. Well, that means you know this angle here. From a straight line is 180 degrees. I'm sorry, let's call this 90 degrees from here to here. 90 minus 54, the complementary angle. Whoa! Courtney must have had to bounce out and come back in. So I've already got you here. Let me let you back in again. Okay. The complement of 54 would be 36, right? So this angle down here we know to be, or can calculate to be, 36 degrees, because 36 and 54 makes 90. Okay. Now from that, we can determine what that length. Where is my pen? It was here just a minute ago. Oh, there it is. we can determine what B is, which we're going to need to know. We'll also need to know what D is. Because we know this length here, we need to know this length here and that length in order to get what angle. See, we're looking for bearing is this. Well, we can't get that, but we can get that bearing. Okay? We're also looking for C. That is the distance from the point of departure. So this is your C here. What they're listing is C down here. Okay. And C, by the way, is your 90 degrees here. So, but in order to get C, we need to know the total length from A to C. If I could get my pen to show there. Nope. Where is my pen? I can't find it. Oh, there, it's way up there. Okay. From A to C and know B, we can get that distance C from Pythagorean theorem. Okay. If we know B and the total of D plus 40, we can get the angle here. Well, there it is, that angle there. So that's the thing. Let's deal with this triangle. Come on, pen, show up somewhere. This triangle right here. 36 degrees here, which means because that's 90, this one up here is also 54 degrees. Now we don't need it, but we do know that because those are complementary angles too. So to get B, let's go for that first. And we know this 20 nautical miles here, so we know we're looking for opposite, we know the hypotenuse, and we know the angle. So that's going to be a sine function. The sine of 36 degrees is going to be B, which we're looking for, over 20. Okay, which implies then that B is equal to 20 times the sine of 36. So, calculator time again. Okay, almost got it charged. Okay, need to get to scientific mode and do 20 times the sine of 36. So I have to enter the 36. Make sure you're in degree mode. 36. Whoa, I'm in the second mode still. And then do sine and equal, and we get that distance to be, now I'm going to write way more digits than I am justified to do. I'm going to put 11.7557. I'll probably regret that later. I'm going to get extra precision there. Okay, we can do the same thing to get the D down here, except now we're using cosine. The cosine of 36 is D divided by hypotenuse. So let's do that up here. Cosine of 36 degrees. That last sneeze that I had has got my head clearing out now. Where is my pen? Should never have moved. There it is equal to that D time, D over 20 nautical miles. All our measures here are in nautical miles, the length measurements. So D is equal to 20 times the cosine of 36 degrees. Now you probably could have used Pythagorean theorem there. This is probably easier. Okay, so we'll do 20 times, again, the 36 enter first, then do cosine equal, and that gives me that D to be, I'll write it up here, approximately equal to 16.18 nautical miles. Okay, now does that make sense? This angle is less than 45, so that makes this side less than this one because this angle is 54. D is going to be larger. Sure enough, it is. Doesn't prove we're right, but at least we got the right thing. Okay, so now we're going to take this D down here, add it to 40. If I could get my pen. So let's add 40 to this, and that gives us 56.18. Now most of the time I would not be using that many decimals, but I want as much precision as we can. My final answer I'll round to something that makes sense. These are more. Okay, so now we've got this angle we're looking for here, which is not our bearing, but this angle here, this is its opposite side. This number here is its adjacent side. So that we're going to be a tangent. So the tangent of the angle we're looking for, theta, is equal to 11.7557, which is way too many digits here, divided by 56.18. And those are both nautical miles. They cancel out, which is good. So let's do the, I think I'll just go on and add 40 to this that I've got on my screen, and that gives me a 56.18. I'll reciprocate that and multiply that by 11.7557. No, yuck. 11.7557. I shouldn't be carrying around this many digits. That's equal to that. So that's a pretty small number. Now I need to go to my second to do an inverse tangent, because that's what the tangent is. So we'll do an inverse tangent of that, and that gives us this angle here, if I can find it, to be approximately, I'm going to call it 11.8 degrees from the inverse tangent of that number. I didn't have room to write it down. Okay. Well, we subtract that from 90 to get the angle we're really interested in. So do this. I'll change sign and add 90 to that. That gives me 78.18. Let's just call that 78 degrees. Okay, if I could find my pen. Where is the pen gone now? I can't find, there it is. Okay, so this will be 78 degrees, approximately. Okay, so we know the bearing is going to be north 78 degrees west. So that's the answer to the bearing part. Now the distance. That's that 11.7557. Now we could do it with trig, or we can do it with Pythagorean theorem. It really doesn't matter. I'll use Pythagorean theorem. So now I can turn my calculator back upright again, because this is just numerical. Oh no, I will need square roots, so I'll need it this way after all. 11.7557. I have to be very careful when I'm entering. I did it again. 7557 squared. I do have a squared key in this case. Plus, and what was my other? 56.18. 56.18 squared equal, and then take a square root of that, and that gives me, take a square root of that, that gives me that gives me C to be approximately, C is going to be the distance part, approximately 57 nautical miles. Okay. Now I've rounded way more reasonably than the book did. But let's see what they got. Well, let's see what they got. Okay, let's take it through here. Now, they introduce all these names, and if this helps you see it and understand it better, by all means, use it, okay? But, frankly, it almost makes it more confusing to me. I mean, I know what they're talking about, but why go through renaming everything? Why not just use the picture? But I guess they can't use the picture. For the triangle BCD, so we're going back to this one. This is where we started, this one here. BCD, that's where we started too. Okay, for that triangle, we have that the angle B down here was the complement of 54 degrees, which is 36 degrees. So 90 minus 54 is 36. That's exactly how we started. Now the two sides of that triangle can be determined first from the sine and cosine, with B being the opposite side of that 36 degrees, so that'll be the sine of 36 would be B over 20, which would be then 20 times the sine of 36 will be B, and that's what they do here, and the cosine D would be the 20 times the cosine of 36 degrees. So I'm not going to flip back and forth. That'll get you dizzy, okay? So we'll calculate those. Well, they haven't calculated those. Then for the triangle ACD, I guess we knew here's A, here's C, and there D. That's the one that's going to give us the bearing angle and the hypotenuse. So that's what we're interested in. For that, the opposite side was B, and the adjacent side was your D plus 40, which is what we did. And opposite over adjacent would be tangent. So the tangent of the angle A, which is not exactly what we're looking for, but we're looking for the complement of that, but we'll get that first. That gives you that. Okay, so that'll be, now they put it all at once. 20 times the sine of 36, that's your B, divided by 20 times the cosine of 36 here, plus 40 from there. To me, this is pretty complicated. I think the way we did it makes more sense, but either way works. If you like this better, go for it. That gives you the tangent of that to be about 0.209, blah, blah, blah. Now take the inverse tangent of that, arctangent of that, that gives you the angle A, and that is about, oh my goodness, why in the world did they go to radians? Well, because they said inverse tangents always uses radians. Guess what? Your calculator doesn't care. Since everything else is in degree, why don't you stay with degrees? But they're going to change the degrees in a minute, so let's see what they got. But every time they make a change like that, you're approximating, you're introducing more calculation error. Okay, so anyway, let's go to that. That would be about 11.82 degrees. What did we say it was? I hope we said about 12. Let's see what it was. We said 11.8 is what I did. And that, I'm pretty sure, was 11.82 would do. Okay. You don't have justification for that many significant digits. I put 11.8, which I thought was a stretch. I think 12 would do. So the angle with the north-south line would then be the complement of that, which is 78.18, which I ultimately said was about 78 degrees. Okay? So the bearing is north 78 west, and that's what we said. And then what was the C? Well, they went and did the trig function. I did Pythagorean theorem. They did the trig function. Let me show you that. That if that's the hypotenuse, and you know this down here, or no, they knew this over here, which is a calculated value, that's the opposite side. They round it off here, so that's going to give you an error, but just a little one, okay? And now that you know this, but that's a calculated angle, so that will give you a good approximation. We said 57 nautical miles when we did the Pythagorean theorem. Let's see what they did when they did it their way. Okay. So they did 20 times the sine. Okay, they go back and put all their numbers in, which keeps them from having as much round off error. Divide that by the sine of this thing, which was still a round off error, and that gave us about 57 nautical miles. So it works whether you use trig functions or use Pythagorean theorem. Both ones work. So that was example 5. How are we doing on time? We just ran over 2 minutes. Sorry about that, but there'll be no extra charge. We'll start next time with harmonic motion. Top of page 331. We almost finished this section. Okay. Well, we got a few more examples to go. Homework exercises for this will be 4.8. You can do any of the odds 5 through 11. They're all at Calc Chat, 9's at Calc View. Either 13 or 15, both at Calc Chat, 15's at Calc View. Any of the odds 17 through starting on page 334, 335, 336, and 337. So I started saying 17 through, wow, it goes on and on, through 43. Any of those odds, 17 to 43, that goes 335 and 336. Then they're all at Calc Chat. 45 or 47, they're both at Calc Chat. 49, that's at Calc Chat. 51 or 53, both at Calc Chat. Wait, hold up. Stop at 43. Sorry about that. From there on is simple harmonic motion. We'll get to that next time. Okay, now here's the question I have to pose before you now. Okay, we're almost through with chapter 4, which means we're almost ready for the second test. Not quite, but close to it. Do you want me to go on and post it today so you'll have the weekend to work on it? Or do you want to just hang off and me post it on Tuesday when we finish the chapter, and then I'll post it then? It doesn't matter to me. Do any of you want it posted now so you can work on it this weekend? If you're not finished with the first test, you can just ignore it until you finish the first test. But please finish the first test so you can get going on the second one. Okay, I will post it. It'll be later today. I won't be able to post it now because I've got another class starting in now 10 minutes. Okay, so I'm not going to have time to post it now, but I will post it either around midday-ish. I have a little bit of time, and I also have some time maybe at the end of the day. But I go until 7:45 today, so I won't have a lot of time. I won't be very coherent then. But I'll try to post it between 1 and 3 if I can. All right, any other questions, issues, concerns, thoughts? Okay, I'm going to stop sharing because I'm sick and tired of sharing. We got up to 11 students today, or now, but some people I think have already left. So unless there's some questions, I'm going to end the meeting for all of us. So take care, folks. Be very careful. Be safe this weekend. Know it's going to be a beautiful weekend, but keep your guard up. The virus is still there big time. As you may have heard, Coach Nick Saban now has it. And I noticed him in the game Saturday. He always kept his mask on. So if he has it, I bet you some of his staff has it. I bet you some of the players have it. So, hey, it's going around, people, big time. Take care. Be safe. We'll see you on Tuesday. Okay? Bye-bye.